This video lecture is meant to cover the information found in Unit 14, Solutions and Equilibrium. And this video lecture specifically is going to cover the information regarding the concept of equilibrium. And we're going to start out today's lesson with a video that comes to us from YouTube.
A chemical reaction at constant temperature in a closed system is in a state of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic means the reaction occurs in both directions. Equilibrium means there are constant concentrations of both reactants and products in the system. Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed in the breeze. This continues until the towel is dry and can be represented by a simple chemical equation. This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel. At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow. Dynamic equilibrium only occurs in closed systems.
So what we have just seen is that in a reaction that is at equilibrium, it has to be in a reaction that is reversible, meaning that if you have a reaction with nitrogen and hydrogen forming ammonia, at the same time in the same reaction vessel, you will have ammonia breaking down into nitrogen and hydrogen. And so according to the video, it was described as when the forward reaction rate is equal to the reverse reaction rate, the reaction is said to be in equilibrium. A two-way arrow is used, something like this. When the reaction is in equilibrium, some reactants and some products are both present in the equilibrium system at any given time. What equilibrium does not mean is that the amount of reactants is equal to the amount of products. That is not a true statement. Equilibrium does mean that the forward reaction rate is happening at the same speed as the reverse reaction rate. Now, once you have a system at equilibrium and it is subjected to a stress, the system will react in such a way to reduce the stress. This makes sense. If you're stressed out about something, you do something to help you reduce that stress. In chemistry, this is called LeChateliers principle. So, what is a stress for a chemical system? A stress is any change to the reaction that leads to a disturbance of the equilibrium. And this can happen either from adding reactants or products, or if you change the temperature, or you change the pressure. We're not going to get too involved in the discussion on the changes of pressure. We're going to focus on changing the amount of reactants or products, and we're going to focus on changing the temperature and what those stresses do to an equilibrium. So if a stress is induced, that stress needs to have some sort of counteraction, right? So to counteract the stress, the equilibrium will either do one of two things. It'll either increase the rate of the forward reaction to compensate, and when the reaction increases the rate of the forward reaction, well, that means you're going to get more products, and so we say that the equilibrium shifts to the right because, you know, the products are on the right side. Or, if that's not a way to counteract the stress, the equilibrium system will increase the rate of the reverse reaction. If the rate of the reverse reaction happens, then you're going to see more reactants formed. And we say that that's a shift to the left because, you know, the reactants are on the left side of the equation. And this will happen until a new equilibrium is reached. You're going to see an equilibrium system today that will be demonstrated in this video, and it involves two complex ions of cobalt. The one on the left that's considered on the reactant side is pink, and what we say that, it's a cation, so that's the other way to help you remember the cation is pink. It's on the left side, so it's a reactant. And the other form of the cobalt ion is an anion, and it's blue. So we can tell if we have more reactants present because the solution will be pink, and we can tell if we have more products present because the solution will be blue. Now notice, also on the reactant side are some chloride ions, and also on the product side are some water molecules. So pay attention to that as we go through this video demonstration. This is the solution that we're going to be working with. It is a cobalt chloride hexahydrate solution. It's dissolved in ethyl alcohol, so this is the symbol for ethyl alcohol. And so looking at this, we put a little bit of that cobalt solution into this test tube. And if we're looking at this equilibrium system in the test tube, which ion is present in greater quantity, the pink cation or the blue anion? Well, clearly, if you're not colorblind, we can see that it is blue, so we have more of the anion present. Now there's some words that are off the screen down here, but those words are reading. Does that mean that the blue anion is the only type of cobalt ion present in this solution? And what you have to understand about equilibrium, just because you see it's blue doesn't mean that there's any pink ions in there. All right, so what we have to realize is that at equilibrium, a true equilibrium, you're going to have both reactants and products present. All right, but because we see it blue, we know that there are more of the anions present. But we are of the understanding that these pink cations are present in some quantity inside this reaction vessel. All right, we are going to apply some stresses to this equilibrium, and we're going to see what happens. So what you're going to see in the next couple of video demonstrations is you're going to see LeChateliers' principle in action. We're going to cause some stresses and try to understand why the equilibrium behaves the way it does. How does the equilibrium counteract the stress that was applied? So our first stress is we're going to change the concentration of a reactant or a product, and for the specific example, we're going to add water. Okay. Well, find water in the equilibrium in the equation. Right? You'll see water all the way over here on the right. So my question to you is, will we be adding a reactant or a product to the equilibrium system? And you are correct if you are saying that you are adding a product. Okay. So what should happen? Let's see what happens. We can see here water is being added to the blue ions, and immediately the solution starts to turn pink. So when you add this product, all of a sudden there's too many products. The added water will react with the present blue anions, and they will react to form more reactants. Right? So the stress here is explained on this slide. What is the color change after the water is added? Well, it turned pink from blue. Which complex ion is favored by the addition of water? Well, the pink ion is the one that is now favored because that was the one that was produced. So the COH2O6, the cation. And because more of this pink ion was produced, we say that it shifts to the left because it made the stress cause the reaction to produce more reactants. So do we say the reactants or the products are favored? Well, if it's shifting to the left, then we say that reactants are favored. So here's the explanation. The stress was that we added a product. The relief is that products need to be reduced. How does that happen? We are going to have to use up product to make reactants. So the added water gets used up with the blue anions, turns them into chloride ions and the pink cation. Right? So the net effect is that the added products get reduced, but the result is that the pink ions were produced in a greater quantity. All right, let's take a look at this next stress. we're going to change the concentration of reactants or products again. Specifically, the stress we're going to do is we're going to add hydrochloric acid, which dissociates. It breaks apart into hydrogen ions and chloride ions. So when we say we're adding HCl, we're adding both hydrogen and chloride, but the ion that's really of interest is the chloride ion, because that's the ion. We don't see hydrogen ions individually in this equation, we just see chloride ions. So adding HCl is like adding chloride ions, and since we see chloride on the left side of the equation, we know that we will be adding a reactant to the equilibrium system. So if we're adding a reactant, will it turn the blue solution pink, or will it turn the pink solution blue? Let's take a look. We're going to try it to both the pink solution and the blue solution. Before I show you this video, just to show you this blue solution right here, this has both pink and blue ions present. Currently in the left test tube there are more blue ions than pink, and in the right test tube there are more pink ions than blue. Right, so we're adding HCl. And as we add chloride ions, the blue solution appears to stay blue. But as we add the chloride ions to the pink solution, it turns bluer. It doesn't turn as deep a blue, so there's not as many blue anions present as there on the right tube as there is in the left tube, but it definitely turns some of the pink ions into the blue ions. So let's go take a look at this next slide to help explain it a little bit. So what was the color change after the HCl was added? Well, the pink turned to blue. Right? So what happened was the added chloride reacted with the pink cation, and it produced more of the blue anion and some waters, but we couldn't really see that because water is not a very visible product in this situation. So which complex ion is favored by the addition of HCl? Well, the blue ion, and that would be the COCl4 anion. Is this a shift to the left or to the right? Well, since we produced more product, we say that it is shifted to the right. And when we say it's shifted to the right, what that really means is that the products were favored. More products got produced as a result of the stress. The stress we saw here was an addition of a reactant. The relief, you need to somehow reduce the reactant. The only way you can reduce reactant is to use up those reactants, and as a result, it makes more products. So that's what happened in this particular stress. All right, in this next demonstration, we are going to change the concentration of reactants or products again, but this time we're going to do something a little different. Instead of adding a reactant or product, we're actually going to remove a reactant or product. So let's see what happens. How can we remove one of these products? It's not like you can go in with tweezers and pluck things out. So we have to chemically remove some of these participating substances in this equilibrium. So here's what we're going to do. We're going to add acetone, which doesn't sound like we're removing anything, but the acetone binds with the water and makes it unavailable. So in effect, by adding acetone, we are removing water from the equilibrium system. So let's see what happens when we remove water. Will we be removing a reactant or a product? Well, since H2O is on the right side of the equation, we see that we are removing a product. Let's see what happens when we add acetone. Will a pink solution turn to blue, or will a blue solution turn to pink? So there's the acetone going into the blue solution, and it stayed blue. And there's the acetone going into the pink solution, which turned it blue. So removing water, the product, seemed to actually make product. Okay, let's take a look at this next slide to try to explain it. So the color change that we saw after the acetone was added is it made the equilibrium turn blue from pink, which means that the complex ion that was favored is the cobalt chloride anion. And since that is a substance that is on the right side of the equation, that's a shift to the right, and we say that products are then favored. All right, so what we can see in this get this darn thing out of the way. It's such a pain. The stress here was that we removed a product. We removed water. So if that's the stress, we have to counteract that. And if products are removed, the equilibrium is going to try to replace product. The only way that you can replace product is to use up reactants to make more products. So that's how that works. If you remove something from an equilibrium, the equilibrium system is going to respond by trying to make more of the thing you just took away to try to keep itself into balance. All right, so we just saw what happens if you remove a product. Let's see what happens if we remove a reactant. So we're going to try to remove this chloride, and here's how we're going to do it. We can't physically take it out by filtration or picking it out individually, so we have to chemically remove it from the system. And to do that, we're going to add silver nitrate. And the silver ions that we add are going to bind with the chloride ions, these guys right here, and remove the chloride ions from participating in the equilibrium. So, will we be removing a reactant or a product? Well, since chloride ions are on the left side of the equation, we will be removing a reactant. So let's see what happens when we add the silver nitrate to the blue solution. We'll see some cloudy precipitate being formed. That's the silver chloride. That's the precipitate that's binding the chloride and taking it out of solution. All right. When we add the same substance to the pink solution, it turns cloudy, but it stays pink. The blue solution turns cloudy and turns not quite as pink as the pink solution, but it does become more pink and less blue. So the solution, by removing chloride, by removing a reactant, we have now made more reactant. Let's take a look at the slide that explains why. So the color change that we saw after the silver nitrate was added is that the solution turned pink. The complex ion that is favored by the addition of silver nitrate is the pink cation. And since that is on the left side of the equation, we say that's a shift to the left, and reactants are favored in this situation. So the stress was that we removed a reactant. The relief is to replace the reactants that were removed, and the only way a chemical equilibrium can do that is to use up the product to make reactants. All right, so in this fifth demonstration, the stress is going to be to change the temperature. And to change the temperature, we have to add something to our equation. We have to see whether or not this equation is endothermic or exothermic. So I'm adding the heat term to this equation, and we see that the heat is on the left side of the arrow. When you see a heat term, whether it's the word heat or energy, or if you see an actual value of energy, an actual quantity of energy on the left side of the equation, we know that that equation is endothermic. So that means we're going to treat heat as a reactant, because the heat term is on the left side, and anything on the left side is a reactant. So when we heat the equilibrium, we're going to see that what we are really doing is we are adding a reactant. All right, so let's take a look at the video and see what happens. So adding a reactant means the pink solution should turn blue. And you can see here the equilibrium system is being put into a beaker of hot water, and almost immediately it turns blue. So we do see that adding a heat in this particular equilibrium system, because heat is on the left side, we're adding a reactant which causes the equilibrium to shift to the right. So after we added heat, we saw that the color change went from pink to blue, which means that the complex ion favored by the addition of heat was the cobalt chloride anion. That's the blue one. And because that substance is on the right side of the equation, it's on the product side of the equation, we say it is a shift to the right. Well, let's go ahead, and we are going to now take that solution, that equilibrium that just came out of the hot water bath, and we are going to put it into a cool water bath. So now we are changing the temperature. The stress is now a cool water bath, and asking ourselves to look at this equation again. Is this reaction endothermic or exothermic? Well, it's the same equation, so it's going to continue to be endothermic. We see the heat term on the left side, so that means it's endothermic, and which means that we're going to treat heat as if it were a reactant. So if we are cooling the substance down, that means we are removing heat. All right, so now we're going to be removing a reactant from the equilibrium system. So let's see what happens when we remove the heat. All right, so we've just taken this solution out of a hot water bath, and we're putting into a beaker of water which was just taken out of the tap. It's not iced down. It's not particularly cold, but it is cooler than the hot water bath. And so as it's agitated and stirred and mixed up here, we can see that the blue equilibrium does indeed turn pink. So the color change after the heat is removed is it turns to pink, because as we take heat away, the equilibrium will shift to replace the heat that you just took away, but in the meanwhile it'll also produce everything else that's on this side of the equation. So the complex ion that's favored in this particular stress, the removal of heat, is the pink cobalt cation, which means because it's on the reactant side, it is a shift to the left. All right, summarizing this whole LeChateliers concept. If you add a chemical which appears on the right side of an equation, it will shift the equilibrium to the left side of the equation. Add something to the right, it'll shift to the left. If you add a chemical which appears on the left side of an equation, it will shift the equilibrium to the right side of the equation. Add something on the left, the equilibrium will shift to the right, making more product. Removing or decreasing the concentration of a chemical which appears on the left side of an equation will shift the equilibrium to the left. So if you removed from the left, the equilibrium will shift to the left. If you remove or decrease the concentration of a chemical which appears on the right side of an equation, it will shift the equilibrium to the right side of the equation. If you remove from the right, it'll shift to the right. And again, by left we mean reactants, by right we mean products. This video lecture has meant to summarize the concept of chemical equilibrium and LeChatelier's principle, which once again says if an equilibrium is subjected to a stress, the system will react in such a way as to reduce the stress. All right, we'll do some practice with this where you can put LeChatelier's principle into action, where you can actually try to predict what will happen if the equilibrium will shift left or right. So at this point, I will see you in the classroom.